Okay, everybody, let's go. I think it's 2 or 3 minutes past the hour, so we are almost on time. And today we have the third colloquium in this semester's series of the Heidelberg Joint Astronomical Colloquium, jointly organized between the 6 institutes in Heidelberg. And today we have Keith Hawkins, who's traveled across from the USA. I think you just arrived a day and a half ago. And he's hosted by Hans-Walter Rix at the Max Planck Institute for Astronomy. So I'll pass over to Hans-Walter to introduce Keith.
Thank you. Yeah, I mean, it's a great pleasure, Keith, to see you here, and for me to introduce Keith Hawkins as today's speaker. I'll say a few words about Keith's work in a second. Keith started out university at Ohio University, the other older university in Ohio, then did his PhD with Jerry Gilmore at Cambridge, which perhaps set him on that path that you see here in this title. After that, he was a Simons Junior Fellow at Columbia University, and for the last 4 or 5 years, he has been on the faculty at the University of Texas in Austin, and much of Keith's work has revolved around stellar spectroscopy, doing that right, and learning about the galaxy. So Keith, I'm excited to hear from you.
Okay, so I'm Keith Hawkins. I am an assistant professor of astronomy at the University of Texas. And what I'll be talking about today is some of the work that my group does on galactic archaeology. So hopefully, you know, I'm guessing not everyone here is a galactic or stellar astronomy. So I'll talk a little bit about why I think it's interesting and important, some of the big questions, and some of the things that we're doing in my group to answer those questions. So whenever I start a talk, a public talk especially, I always ask roughly the same question. Things like, you know, when you look up, what do you see? And if you're talking to 5th graders, or, you know, they would probably be of order, I don't know, 8 or 9, they'll say they see the sky, they see the ceiling, the lights. But if you go out to a dark night sky, you'll see something that looks like this. And this is, of course, the Milky Way galaxy. And when I was starting graduate school, I was really excited about the Milky Way, and in particular, questions about how do galaxies in general form, how do they evolve, how are they structured. And as a galactic archaeologist, my goal is to answer these fundamental questions, but answer them using the Milky Way as a laboratory for studying galaxy formation questions. So that's what galactic archaeology is all about, using stellar fossils and the chemistry encoded in those stellar fossils, and the kinematics and the spatial positions of those stellar fossils to answer these fundamental questions about galaxy formation. And then as I grew in my career, I started asking questions about how the elements are made, and how do stars and stellar systems form, and how do stars get accelerated to high speeds. And then I realized I have way too many questions in my head, which is why I became a professor, so I can have students that will answer these for me. So these are some of the big questions that my group really tries to address. And to do this, we of course use the Milky Way as a laboratory. And so this is the best reconstruction of the Milky Way that we have to date. This is a reconstruction based on the Gaia spacecraft. I probably don't have to talk too much about Gaia, since there are many people that work on Gaia in this audience. And so the Milky Way has a structure to it. It's got a bulge in the central parts of the galaxy. It's metal rich. It's got a thin disk, which is you know, very thin and made of young metal rich stars. The sun actually was born and raised, if you will, in the thin disk of our galaxy. It's got a thick disk, which is a thicker component, a thicker disk component, more moderate metallicities, lower metallicity, and older stars. And then it's got a halo on the outskirts. Now, I do want to note that there's a debate about these components. This is just a classical image of our galaxy, but there are some debates about these components. For example, the halo, depending on who you talk to, is an inner component and an outer component. And that inner component is likely in situ and accreted, and the outer component is likely just accreted. It kind of just depends on who you talk to, and I put some of the references there. And I put this up primarily for usually, especially when I'm giving talks in the United States. And the reason for that is because one thing I realized when I was an undergraduate at Ohio University was that for whatever reason, the United States and European astronomy went in two very different directions, it seems to me at least. When I was in the United States, I was told that when I was going to graduate school that everything in astronomy more or less is solved except for exoplanets and cosmology, and that was it. And the Milky Way and stars was kind of a dead problem. And then I came to Europe in part to get trained because there was a lot going on in stellar astrophysics in Europe, a lot going on in galactic structure, and so that's the reason why I came to Europe to get trained. I also want to note for those of you that don't work on the Milky Way, I often like to think about the galaxy in terms of breakfast food because I really enjoy breakfast. So if you're not familiar with the Milky Way, the best way to think about this in terms of breakfast food is the thin disk is like a French crepe. The thick disk is like a fat American pancake. The halo on the outskirts is like if you take that French crepe and that fat American pancake and you deep fry it, you batter it up and you deep fry it, that batter on the outside is the stellar halo, and then if you put a big ball of butter in the middle, that's the bulge. It's extremely unhealthy. You probably shouldn't eat that. But that is the Milky Way in a breakfast food analogy. So there are, these debates are still under, or these components are still under debate. It's something that we're still trying to figure out. And Gaia and large-scale spectroscopic surveys are enabling us to really separate out and piece together the structure of the galaxy. And we do this using stellar fossils. I often will say stars are fossils for two reasons. The primary reason why stars are fossils, though, is because the chemical makeup on the surface of the star, generally speaking, doesn't change over the course of its life. And so what that means is that barring some light elements like carbon, nitrogen, oxygen, and lithium, most of the elements on the surface of the star, heavier elements, iron, cobalt, nickel, chromium, these types of elements, remain constant even though the star is aging. So the star may experience different perturbations that will change its dynamics, change its orbits, change where it's located in the galaxy, but the chemistry will always roughly remain the same. So you can use the stars in the galaxy not only as tracers of the underlying components of the Milky Way, but also as historical tracers to what the universe was doing when those stars were born. And this is an incredible time to get involved in galactic archaeology. That's another reason why I came to Europe to get trained, is because all of these large-scale surveys were either going on or started around the time I started my PhD in 2013. We had the GAISO survey, the GALA survey, the Apogee survey, and the RAVE survey, all that were kind of going on when I started, collecting high-resolution spectra, moderate to high-resolution spectra for something like 100,000 to 1 million stars. You also have Foremost coming up and all these other surveys coming up that are collecting millions of spectra. And we also have Gaia that allow, the astrometric mission and photometric mission Gaia that was providing us with, or about to be providing us with astrometric information for something like 1.6, 1.8 billion stars. And when you combine all this information together, you not only have the 3D positions of the stars from Gaia, the velocities from Gaia plus the spectroscopic surveys, you also have the chemical abundance information. So now you're in this unique space where you have 3 dimensions of velocity, 3 dimensions of position, so you have full 6D phase space, and chemical abundances for up to 25 elements for something like 100,000 to 1 million stars. And it's with that information with which then you can answer questions about galaxy formation. And it's really the only system that you can do that for. You can't do this in Andromeda. You can't do this type of thing in galaxies at high redshift. The Milky Way is one of the cases where you can do this, and that's why I study the Milky Way. Now, Gaia is amazing. And thank you to all of the folks in the audience that have worked on Gaia and from its inception onward, because Gaia really has transformed, I think, and revolutionized astronomy the way that it said it would back when it was being launched. Gaia was, of course, launched in 2013. Its first data release was in 2016. Its second was in 2018. EDR3 was in December 2020. And now I put a Christmas hat there because for me, Christmas morning is June 13th. Unfortunately, for you all in Europe, it's great. It's like noon, but for me, it's at like 4 a.m. That's going to be hard. But Christmas is going to be June 13th for us. And this is giving you an idea, this taken from ESA, an idea of what we already have with Gaia. Now, I don't know if there are graduate students or postdocs in the room, but I wanted to stop here and also mention my own career path because when I was a graduate student, I remember my PhD advisor more or less telling me the best way to do...
Could you say that again? I'm having trouble hearing you.
Apparently Siri was having trouble hearing me. So my PhD advisor told me one of the best ways to kind of evolve your career is to, if there's a new mission coming out like this, is to basically follow the mission through your career, which is exactly what I did. So I started my PhD in 2013. 2.5 years later, I finished my PhD when the first data release occurred. So I started my first postdoc right as DR1 came out, or TGAS. And then DR2 happened right when I got my first faculty position about a year or two later. And then now I'm actually going up for tenure promotion this year as well. So like I literally followed every data release from launch to data release 1 to data release 2 with a new stage of my career. So that's one way to kind of evolve yourself in the career. Now, Gaia is going to, with Gaia plus all of these large spectroscopic surveys, we're kind of in this completely data-rich, unique era to do galactic archaeology and really uncover the structure and nature and formation and assembly history of our galaxy, because we have so many dimensions of information for so many stars. And what I'm most excited about in this upcoming data release is the spectra releases. Since I'm actually mostly a stellar spectroscopist, I'm mostly excited that the DR3 and the DPAC will be releasing BPRP spectra for 100 million stars, and RVS spectra, so moderate-ish resolution R of 11,000 spectra for like 1 million stars. And with that, you can actually derive astrophysical parameters, temperature, surface gravity, metallicity, and most importantly for me, chemical abundances. Because it's the chemistry of the stars, as I hope to kind of convince you by the end of this talk, it's the chemistry of the stars that can really tell you important and key information about where the star was born, and therefore allow us to backtrack how the galaxy was assembled. Okay, so before I get into the rest, are there any questions so far on what I've said? Great. Don't see any. Okay, so for me, the chemistry is where it's at. And to get everyone up to speed on chemical evolution of the galaxy, here's a nice image, I think taken from Anna Frabel, which kind of consolidates all of galactic and universal chemical evolution into one slide, into one nice picture. So at the start of the universe, you have the Big Bang, and then you have basically hydrogen, helium, and trace amounts of lithium, and that's it. The first generation of stars, the so-called population 3 stars, then form. We don't know what they are. We don't really know what they're like. We've never seen one, obviously. But we think they're probably fairly massive. And these massive stars die very quickly. They explode in either supernovae type 2 or hypernovae or parent stability supernovae or some variant flavor of supernova explosion. They produce then the first set of elements that come out, which are the alpha elements. The alpha elements are elements that are formed by alpha capture or helium capture. These are things like magnesium, silicon, sulfur, oxygen, and so forth. And they are dispersed into the interstellar medium by type 2 supernovae. So these alpha elements come out on relatively short timescales. From that polluted material, a new generation of stars form. Those new generation of stars will form, they live, they die, they explode, they disperse their nucleosynthetic guts back into the interstellar medium in the star gas cycle, and you form a new set of elements, a new set of stars, and over time you build up this global metallicity, the elements on the periodic table. Now, at later times, when you have white dwarfs forming from low mass stars, those white dwarfs can then go supernova, regardless of whether it's double degenerate or single degenerate. They will go supernova and produce and disperse primarily the iron and iron peak elements. These are things like iron, chromium, cobalt, nickel, and so forth. Then our manganese, chromium, iron, and nickel. They will be dispersed into the interstellar medium. And so type 1a supernovae produce these iron peak elements on longer time scales. And then at even later time scales, you can have neutron star mergers, or very, very massive stars that go supernova, which will then produce even heavier so-called R process elements like uranium, thorium, and europium. Okay, so this is just a general idea of how galactic chemical evolution happens. This is sweeping a lot of stuff under the rug and making it oversimplified, but essentially the first set of elements that come out are alpha elements, the next set of elements that come out are the iron peak elements, and the third set of elements in tandem that come out is the so-called R process elements. Okay, and so this led to a particular diagram that you will see classically in almost all galactic archaeology studies, called the alpha metallicity diagram, or as I've seen on Twitter, it's now being called the Tinsley-Wallerstein diagram. And on the x-axis, you have the metallicity of the star, so the iron to hydrogen ratio. On the y-axis, you have the alpha to iron ratio. So this is the global metallicity. This tracks with global metallicity of the star. We just call this metallicity for short. It's in logarithmic form, and relative to the sun. So that means that the sun sits here at 0, 0. Minus 1 means it has 1/10 the iron content of the sun, and so forth. On the y-axis, you have the average of the alpha elements, like magnesium, silicon, calcium, oxygen, sulfur, or whatever you can measure, and divided by iron. And so this ratio is a short time scale to a long time scale. So what that means is that these stars up here that have high alpha and low metallicity, they've been polluted by type 2 supernovae. So they're low metallicity because they've only been polluted by a handful or so type 2 supernovae. But because they've been polluted by type 2 supernovae, they have lots of alpha and not so much iron. So they have high alpha, low iron, so they have this value is large. As type 1a kick in, the delay time for that is about a gigayear, but that's debatable. What will happen is that you'll start producing more and more iron as type 1a start kicking in more and more. That will turn that ratio over. So there will be a knee in the alpha metallicity diagram, this kink, and that kink happens about a delay of about a gigayear or so. And so stars that are old versus stars that are young sit in different regions on this diagram, and that's the reason why the Milky Way can be separated into its different components by this Tinsley-Wallerstein diagram, where the halo is metal-rich and metal poor and alpha-rich, whereas the thin disk down here is metal-rich and alpha-poor. Okay, so this will become more useful towards the end of my talk. One other really important note about why this diagram is super exciting and interesting is that not only can you distinguish between the different components of the Milky Way, but because the delay time between type 2s and type 1as is about 1 gigayear or so, the metallicity that you can build up to before that gigayear happens and before you get the turnover depends on the mass of the system. The more mass you have in the system, the higher the star formation rate can be. The higher the star formation rate can be, the more iron you can produce before the type 1as kick in and you deplete your ratio, your alpha to iron ratio. And so what can happen is that if this, at a constant metallicity, low alpha means you were formed in a low mass system, a dwarf galaxy system. And this is actually one of the primary ways that we have been able to find out that the Milky Way has accreted and eaten through galactic cannibalism, different material. Just to give you an idea, this is just a cartoon that I've drawn here, but this is actually what real data from a large-scale, the Apogee survey, for example, a large-scale abundance survey of stars shows us beautifully this thin and thick disk with the halo and accreted halo over here. Okay? So my group uses chemical compositions, spatial positions, and kinematics and dynamics of stars to essentially identify and answer questions about galaxy formation and the buildup of the Milky Way. I've kind of shown my group here. So I have I had four PhD students, one graduated and went on to Durham as a postdoc, one postdoc and now three graduate students, and I've worked with a total of about 9 undergrads, so kind of a large group or so at UT. And some of the questions that we work on can be broken into stars and the assembly of the galaxy and the stellar side. What I'll be focusing on primarily in this talk is chemical tagging and the use of chemical tagging to try and back out the assembly history of the galaxy. So I'll talk a lot about that. But there are other things that I have worked on in my group because my interests are quite broad. Things like where does life in the galaxy exist, and particularly tracking the element phosphorus. So for those of you that were in the stellar evolution or stars group this morning, I talked about that at the stars group. But I'm also interested in how the components form and how the Milky Way assembles itself and all kinds of other things. So there's a lot of probably collaboration points with folks in the audience on some of my interests. But I'll primarily focus today on the origin of the fastest stars and chemical tagging. Okay, so my group works, the way I've structured my group is I work on the Milky Way as a whole, but what I've decided to do, at least for the first part of my career, is I put each graduate student on a different component of the Milky Way. So my graduate student, Maddie Lucy, has completed a survey of the galactic bulge, and particularly looking at metal poor stars in the bulge. Don't have time to talk about that, but Maddie's an incredible student, has written, she's written 4 first author papers as a fourth-year student. Drea Carrillo worked on the galactic halo, and now she's at Durham, continuing that work on with Alice Deason. And I have Zach Moss, who's my postdoc, Catherine Benea, and Tyler Nelson, who are both graduate students with me, working on the galactic disk. And so what I'll focus on for the first part of this talk is the kind of stuff that we're working on, particularly in the galactic disk of the galaxy. And the question that I was most interested about when I started my faculty position is this idea of chemical tagging. So I'll talk about what chemical tagging is and how we can use chemical tagging to map out things like how the Milky Way came to be, or the origin of weird stars, or all kinds of other things. So as a galactic archaeologist, we have tools with which we can actually try to piece together how the Milky Way came to be. And there are 2 primary tools that I have been developing and working on in my group: dynamical tagging, which is taking the dynamical information, the orbital information from stars, and then trying to backtrack where they came from based on the dynamics. That's called dynamical tagging, and you can do that now pretty well thanks to Gaia. There is a lot of difficulty with doing dynamical tagging for old stars, but for young stars at least, you can probably do this with Gaia. And chemical tagging, which I will focus on primarily. But chemical tagging is this idea that you can use the chemistry of the star to tag where it was born. And what I hope to do as I kind of get further into my career is actually focus on chemodynamic tagging using chemistry and dynamics to actually tag the birth location of individual stars so that we can backtrack and rewind and figure out how the Milky Way came to be. So I'll start with chemical tagging. Chemical tagging is this idea that it came about in the early 2000s from Freeman and Bland Hawthorne. And the idea was simply that imagine you have 2 star systems that are born on different regions of the galaxy. What will happen is that those stars will be born, then they will interact with stuff in the Milky Way and phase mix all throughout the galaxy, so you won't be able to determine where they were born. But if you know the chemical tag, or if you know the detailed chemical pattern of every star in the galaxy, then you can tag where it was born. Kind of like DNA tagging for human beings, right? So imagine, right, I go and get taken a DNA test, and I can figure out X% of my ancestors came from Africa, X% came from Asia, X% came from Europe. Imagine doing that exact same thing, but on a galactic scale, where you're doing this for every star in the galaxy. If you can do that, then you can backtrack and figure out where every star was born, and then from that you can rewind and back out how the Milky Way assembled itself. Now, in order for chemical tagging to work, 2 things have to be true. There are 2 underlying assumptions, underlying requirements. Number 1, stars that are born together have to be chemically homogeneous. That's the tag you're going to use, right? That's the DNA tag. So stars born together have to be chemically homogeneous. In addition to that, stars born in different regions of the galaxy have to be chemically different. So a star born in the thick disk has to be chemically different than a star born in the thin disk, so that you know that they came from different locations. And if you look in the literature, there are 2 different flavors of chemical tagging that tend to permeate. One is strong chemical tagging, which is this idea that you can determine the exact birth cloud that a star came from, given its chemical pattern. And the second is weak chemical tagging, which says, okay, maybe you can't determine the exact birth cloud, but you can determine the component with which the star was born in. Okay, so these are the 2 flavors. And this is kind of an important question at some level, because if you can do, whole surveys, the Galah survey, for example, is built around the idea of chemical tagging. Millions of dollars have been invested in the idea that chemical tagging does work. And so this is kind of an important question, and to answer whether chemical tagging works or not is asking whether these 2 requirements are satisfied or not. And so essentially that's like asking, okay, are two stars that are wide binaries, or binaries are born together, are those 2 stars chemically homogeneous or not? Because on the assumption of chemical tagging, they have to be, right? The answer to this question can either be yes or no. Stars born together are either chemically homogeneous or they're not, right? It's assumed to be yes, not just for chemical tagging, but also for what I would call exotic star characterization. Exotic stars are like M dwarfs. Okay, they're not really exotic, they're everywhere. But it turns out that our understanding of molecular opacities pretty much sucks, And so measuring chemical abundances of M dwarfs is really, really hard to do, despite the fact that exoplanet folks really like M dwarfs because they're easy to find planets around, or easier to find planets around. So if you want to know the chemistry of an M dwarf so that you can know the chemistry of your planet, then what people will do is they will find an M dwarf in a wide binary pair with something that's easy, like an FGK star, and they'll just assume that the M dwarf and the FGK star have the same chemical pattern because they were born together. But is that assumption good or bad? How many people think that assumption is good? How many people think that assumption is bad? How many people don't really know?
How identical does identical have to be?
It's a good question. If for strong chemical tagging to work, identical really means like the 0.01, 0.02 dex level. Weak chemical tagging means the difference between the components. That difference is how good you have to be, how twin-like, so to speak, you have to be in chemistry. That's like 0.1 dex. But what people will generally say is they have to be chemically homogeneous within the uncertainty, where the uncertainties for typical high-res spectra are about somewhere between 0.05 and 0.08 dex. Okay, so a lot of people don't know. Some people say yes, some people say no. All right, well, if the answer to this if the answer is yes, then we're fine, and if the answer is no, well, we're kind of in trouble because people are already doing this and millions of dollars have been invested. Okay, so this is kind of an important question. So let me show you a test case. This is a case from Semyoung Oh's work in 2017. I remember this because we were all huddled around at CCA, Flatiron Institute in New York City. This happened when I was a postdoc. And Gaia DR2 comes out, and in that catalog, folks were finding wide binaries, or co-moving pairs of stars that were moving together, pairs of stars being that they were likely wide binaries born together. John Brewer then goes to his catalog of high-resolution abundances and finds, oh, at least one of these pairs of stars, these wide binary pairs, has chemical patterns that he's measured for both stars from high-res shell spectra. And what you're seeing here is the X over H ratio for different elements for one star in blue and the other star in the binary pair in red. Now, if wide binaries that are born together are chemically homogeneous, the blue and the red line need to overlap with an uncertainty. They don't. And there's a 0.2 dex difference in the elemental abundances. This is a problem. This calls into question whether chemical tagging will work. This calls into question whether stars born together are indeed chemically homogeneous or not. So all this stuff we're doing with M dwarfs, maybe that's not right. So there's a lot of papers that have been written about this topic because it's so important. I've spent a lot of my time writing papers on this, and if this question of whether chemical tagging works is still kind of a confusing one. It's still one that we're still trying to figure out. And an example: does chemical tagging work? If you ask that question to the literature, there's a nice paper from Laia Kesamaquela in 2021 that said, no, it won't work. And it was on the basis, in large part, from Semyoung Oh's work. She went and did that kind of work, or similar style of work, and found maybe chemical tagging doesn't work. So that was 2021. A few months ago, a paper comes out in 2022 saying, actually, it totally will work. So the literature tells you completely different answers depending on which year you're going to ask that question. Okay, so when I arrived at UT, I decided, okay, let's try to test more rigorously the underlying assumptions of chemical tagging. Let's start with the assumption that two stars born together are homogeneous. Semyoung Oh's work shows us that maybe it's not, the Kronos and Krios example that I showed in the previous slide. Let's go and test that for many more pairs of stars and for many more separations. So we did that. We actually went out. So one of the nice things about being at UT Austin is I have access to McDonald Observatory out in West Texas, pictured here. So we went out and tested this exact thing with optical spectra. We obtained very high resolution, very high signal noise optical spectra for wide binaries. This is an example of two of the stars in a wide binary that we actually looked at. And if they're chemically alike, then chemical tagging can work. At least the underlying assumption works. And if they're not alike, chemical tagging can't work. For the spectroscopists in the room, here are 4 wide binary pairs, high resolution spectra of 4 wide binary pairs pair 1, 2, 3, and 4 around 4870 to 4900 angstrom. And the solid line is one star and the dotted line is the other. Now, you don't have to be a stellar spectroscopist to recognize that it's very hard to tell the difference between almost all of these spectra, right? And so that tells you that the chemical composition of these wide binary pairs are almost identical within the uncertainties. So we did this for something like 25 pairs of stars just to see how many times we could get the Kronos and Krios result, and the answer was not that many times. So this is the summary figure from that paper, where on the x-axis you're seeing at different elemental abundances, on the y-axis you're seeing the dispersion of the difference in x over h for wide binaries in red triangles, compared to random pairs of field stars in orange triangles. And in black circles are how well we think we can measure the total uncertainty with which we can measure each element. And you can see that the red triangles and the black circles tend to overlap each other, which means that within uncertainties, we cannot make a distinction between the chemical abundances of the wide binaries, whereas we can distinguish at the 4 or 5 sigma level, or at the 2 to 3 sigma level at least, large differences between the random pairs of stars. Yep.
You've used the composition of the birth material and the composition of the photosphere, which is Spectrum Pro, as being basically synonymous, or they have to be identical, right? To which extent is that actually given, and does this work better if the two stars have the same temperature?
So to answer the second part first, in almost all cases of these pairs, we actually do two stars that have the same temperature within 100 Kelvin, specifically to weed out systematic effects. We do a line-by-line differential analysis as well to also weed out systematic effects on at the line list level. We tried to do very careful work here, and that's why, so their abundance precisions are not too terrible in that regard. Now, in this case, it's n equals 2 pairs that we were working with. And so the idea is that the cloud that formed that n equals 2 pair probably was homogeneous at the level of, on the scale of n equals 2, the particular pair. But at larger and larger and larger scales, when n equals, say, 1,000, when you start going to an open cluster or these long stellar strings, maybe things start to break down.
Isn't there the concept of atomic diffusion, other things that actually cause the photospheric abundance to be a misleading indicator of birth material composition?
Yeah, that's a good question. So you can have atomic diffusion in old stars and radiative levitation in hot stars that can alter very slightly at the 0.05 dex level or so the abundances at the surface level, which can change your assumption about the birth cloud versus what's on the surface now. That A can be modeled, and B, for the purposes of this study, because we're looking at twin stars in stellar parameter space, we don't care so much about diffusion because both stars should have the similar amounts of diffusion. So for the purposes of asking the question, are stars born together homogeneous, that's irrelevant, so to speak. But in the purposes of if we were wanting to know exactly what the chemistry of the birth cloud was, then we would need to go out and model the diffusion effects. Okay, so then we, as a result of this work, we wrote a paper and said, identical or fraternal twins, what is the chemistry of these wide binaries? And we find that in general, by and large, in 80 to 90% of the cases, stars that are born together are chemically homogeneous. And this actually got a little bit of press, in large part because I am a twin. So I was like twin astronomer studying twin stars. I'm a fraternal twin, but it turns out that most of the stars that we studied are actually identical in their chemistry. And so what we had expected was that, okay, this random sample of 25 wide binaries, the separations were not that far. These two stars were fairly close together. They were wide binaries, but they were still bound. And so what we expected was that as we pull two stars apart, the wide binaries apart, so where they're no longer bound, this chemical homogeneity should break down, right? Because at that point, you're just seeing, if you're looking at co-moving pairs of stars that are not bound, you're looking at potentially chance alignments of stars that just happen to be moving together that are not chemically related to each other at all. And so my student, Tyler Nelson, then expanded this study and asked the question, as we take these wide binaries and bring them apart so that their separations go to parsec levels parsec scales, does this chemical homogeneity break down? And the answer is, well, not really. So Tyler went and studied, each one of these blue points is a wide binary from Tyler's study. We ended up getting many more pairs with, in collaboration with Alex G and Wenson Ting from Mike Magellan. And even at separations of 10 to the 6, 10 to the 7 AU, which is like a few parsecs at that point. So these things are not bound anymore. The homogeneity level, so this is the difference in metallicity as a function of 3D pair separation, and the, it's centered around 0 with a dispersion of like 0.05, even at dispersions, or even at separations of a few parsecs. So this is quite incredible. This idea of chemical homogeneity is pretty strong even at co-moving pairs that are separated by relatively large distances. Okay, so then what I started thinking was, okay, so at least for the n equals 2 case, for wide binary pairs, chemical homogeneity or chemical tagging might work because homogeneity is a good approximation. So what about larger n systems? What about open clusters, for example? So this has been studied time and time again. Open clusters are fairly homogeneous, but something unique happened with Gaia data. In the Gaia data came out, and I think DR2, folks were finding these co-moving structures that were like open clusters, except for they weren't spherical-like things. They were like these very long cigar-shaped strings that were elongated by like 400 parsecs at maximum scale. And so the question was, okay, well, are these structures homogeneous, right? We're now probing a much larger n system, and we're probing it on much larger scales. And so the first thing we did was went and looked at Piscerodonis. So this is discovered in Gaia DR2, I think, where they basically take V5 VR, VZ VR, and VZ V5, and if you look at over densities in a wavelet analysis of this particular projection, these 3D velocity projections, you see these over densities. Each one of these over densities is a structure co-moving together. That's why it's an over density there. And they found a particular structure there. And when they plotted it on the sky, one might expect it to just look like a normal open cluster, because that's what all these other ones look like. And when they plotted it on the sky, it looked like this. So this is an elongated structure that's hundreds of parsecs long, right? And it might have these over densities in them. So it's a cigar-shaped like structure that's huge. And simple, the CMD looks beautiful, where all the blue stars are the CMD for this particular thing, all along lie along a CMD. And they were able to measure its age using isochrones at about 1 gigayear. And so maybe you could take an open cluster and shear it apart in a gigayear to that scale. Except for Jason Curtis then went back and said, let me just check to make sure the age is right. I'm going to do this with gyrochronology. So Jason Curtis does this with gyrochronology. So you're looking at effective temperature as a function of rotation periods for different open clusters. So the 620 million year old Persepi, or sorry, the gig-year-old NGC 6811, Persepi here, and the Pleiades here in blue. Now, if it's really a gig-year-old, their argument was the rotation ages should match this sequence here, this 1,000-year-old, or a gig-year-old sequence. Except for all the stars from Piscerodonis are in red stars and are rotating at a rate that is similar to what is expected for a 100-million-year-old system. And so this, they said in this paper, this takes this particular string and makes it one of the closest, youngest cigar-shaped like things in the local neighborhood. It also means at 100 million years, how are you going to take a spherical thing, and shear it apart so that it's 400 parsecs long? Right? It becomes a dynamical challenge to do that. So when this work came out, I immediately said, one, let's go look at the chemical homogeneity, because then we can test it on larger scales with larger n, and let's check the lithium abundances, because then we can confirm, is it young or is it old? If it's young, it should be lithium depleted. If it's old, there should be lithium there. So that's what we did. So we studied the chemical distribution of Piscerodonis. This is the metallicity distribution. And we find that it's peaked at just slightly subsolar metallicities, but its dispersion is 0.04 dex. Our errors are 0.05 dex. So within the level of precision, we would say that it's chemically homogeneous. And this is the lithium abundance as a function of temperature, right? Lithium depletes over time. So this is the lithium as a function of temperature in the several gig-year-old disk, in the Hyades, 600 million-year-old Hyades, and in the Pleiades. And we do find, in fact, that there's enhancements in lithium, which indicates that the structure is young. So lithium allowed us to determine and confirm that the structure was young, and we still see a very high level of homogeneity. So many more strings have been found. Marina Konkel's work and others have been finding these strings left and right using the similar techniques using HDB scan. So there's just a smattering of them. And so we decided, again, let's go and check this on these chemical homogeneity, see if Piceridonus is unique or if this is true across many, many strings. So my student Catherine Manea actually repeated this study, but with Galactic data, she repeated my study with Piceridonus, but on a larger, significantly larger number of about 12 strings. And what she found is that most of those strings, so this is the lithium abundance of each of the different strings that we looked at. They're in many regards, many of the lithium abundances are significantly enhanced in the strings. That tells us that the strings have to be young. They cannot be old, otherwise they would be depleted in their lithium. Catherine's work also looked at the dispersion, the intrinsic dispersion of each string relative to the local dispersion around the string. And this is the dispersion locally divided by the dispersion within the string in each elemental abundance. The gray out region is the region where the string is no longer as homogeneous as the local region. And so she found that there are two groups of strings. There are those that are very homogeneous at the level of open clusters within Galactic, and there are those that are just not homogeneous at all. What this suggests is that some of the strings are likely real, but some of them are likely not real, at least from a chemical perspective. So this is something that we want to test with DR3 when new RVs come out for 33, 35 million targets, is actually to check whether these strings are indeed real from 3D velocity dispersions, and if these ones are not. That would be kind of interesting. So we're going to be doing that as well. Okay, so good. So that tells us that chemical homogeneity is a good approximation at n equals 2 systems. It's also a good approximation at n equals 1,000 systems, even though those systems are on very large scales, on 400 parsec long scales. Now, I have a graduate student that is working with me looking at dynamical modeling. She's actually dynamically modeled these strings and has found from a dynamical perspective that these strings have to form on large spatial scales. They cannot form on the same spatial scales as things like the Pleiades open cluster. But I don't have time to talk about that, but I do have slides in case anyone's interested. The second thing is, so now we're going out in scale. Let's go to one higher scale. Let's go to the galactic scale. So now the question is, are stars at the same galactocentric radius similar in chemical composition, right? Because if they are, that might help us determine on what scales does chemical homogeneity, or stars born together being chemically homogeneous, on what scale does this all break down? So this is one of the last things I'll talk about. So I've been really excited about some work that was going on here, actually. So there was a nice catalog of metallicities for relatively hot, relatively young stars that Mao Sheng published, I think, last year. And one of the things that I thought about was, in this perspective of are stars born together chemically homogeneous or not, is that are stars born at the same galactocentric radius chemically homogeneous or not? And we know that stars born at different radii are different, right? There's a metal gradient in the galactic disk, a radial gradient such that the inner galaxy is metal rich and the outer galaxy is metal poor. But what if we look azimuthally along a given radius? Are they homogeneous, or do you see imprints of the spiral structure? So that's what I went out looking for with Mao Sheng's catalog. There was just simply taking a temperature of, hot stars. So this is the temperature surface gravity diagram of the sample that I selected from. If you select out a relatively high quality sample, this is their galactocentric positions in X, Y, and RZ. So and relative to the spiral arms, the relative locations of the spiral arms here, shown in black. And if you overplot that with metallicity, you see again beautifully the inner galaxy is metal rich, the outer galaxy is metal poor, the plane of the disk is metal rich, the outer galaxy, off the plane is metal poor. So this is all already known. So you can fit a metal gradient to this, and you can determine that you have a negative radial gradient and a negative vertical gradient, and you can measure that, and you can compare it to studies, and that's all fine. You can do that, and that's what we did. That's what I did. I added, you can do errors of both, errors on both dimensions and do this, and you get something like this. So this is the metallicity radial gradient as a function of vertical height for the OBAF stars in Mauching's catalog compared to other studies. So everything looks consistent. So this wasn't terribly exciting. This was just, okay, we see a vertical gradient in the disk, and it's consistent with other studies. But what I thought might be exciting is let's look at the azimuthal variations. And importantly, I was wondering if we take off, so if we take this is our metallicity gradient, or metallicity distribution for stars that are between 0 and 0.3 kpc from the plane. You can see that it's the inner galaxy is metal rich, the outer galaxy is metal poor. So if we fit a model to that and we subtract off this model assumes that at every radius, stars have the exact same metallicity. And that metallicity decreases as you go outward in the disk. So if you subtract off the model from the data, you should just see noise if every star is the same metallicity at a given radius. And the answer is you don't see that. You actually see substructure in the residual, which tells you that there's azimuthal structure in the metallicity gradient in the galactic disk. So depending on what azimuth you are spanning at, looking at in the disk, you see a slightly different metallicity gradient. And what I was hoping initially when I did this was that azimuthal variation would fall along the spiral pattern, but it doesn't. And so we do see azimuthal variations at the 0.5 dex level, 0.1 dex level, and I didn't really understand how to explain it until there was a nice paper from Chris Carr that happened to come out exactly around the same time I was doing this. And what Chris Carr does, Chris Carr is a graduate student working with Katherine Johnson at Columbia. What he does is he takes a simple Milky Way model with a radial gradient, a negative radial gradient, and every star at the same radius is given the exact same metallicity. So it's a very simple model. He then perturbs that model with the Sagittarius dwarf galaxy, and the perturbation causes stars to migrate in and out from their original birth locations. And that, as a result, induces these different metallicities, such that even though every star at the same radius was born with the same metallicity, because of migration of stars in and out of the disk, it induces azimuthal variations. And they find that these azimuthal variations rise and fall across azimuth. The azimuthal variation rises and falls at about 0.05 dex level. If we do this with the data, we find roughly the same thing. Now, this is not necessarily a fair comparison, but it's a kind of instructive that maybe this could be one of the reasons why we're seeing azimuthal variations as perturbations from dwarf galaxies. Okay. So to summarize, chemical tagging requires stars to be born. Stars that are born together have to be chemically homogeneous. We tested this in the wide binary case. That's good. Chemical tagging can work, at least on the wide binary scale. We tested this on stellar string scales, so on much larger scales. We find that the strings are young. We find that they're chemically homogeneous, at least the ones that we think are real. That tells us that chemical tagging can at least work on these scales. But it's right around the scale of the galactic disk where things will become non-homogeneous and where chemical tagging may break down. So that's good. Chemical tagging may work, at least in its weakest form. It's certainly promising. What have we done since then with chemical tagging? I got excited about hypervelocity stars when I was an undergraduate researcher. These are fast-moving stars that are moving so fast they're actually unbound to the Milky Way. It's likely that they're produced by triple body encounters between a binary star system and the supermassive black hole at the galactic center. One star gets captured by the black hole, another star gets ejected at very high velocities. But the chemistry of hypervelocity, or the origin of hypervelocity stars, while they should be the galactic center, dynamical tagging suggests not all of them come from the galactic center. So if you do dynamical orbit integration, you can't get some of them to the galactic center. So where are they coming from? I got an NSF grant basically to do chemical tagging on hypervelocity stars, and we're finishing that work now. The first survey was done in 2018, and the second survey was published by Henrique Reggiani a couple of months, or maybe about a month ago, and my student Tyler Nelson's finishing the last part of that survey. I don't have time to talk about the results of that survey, but suffice to say, hypervelocity stars are a little more complicated in their origin than just triple body encounters with a supermassive black hole. Some of them are extragalactic and some are galactic. In addition, I've also worked very hard recently to use chemical tagging to understand the origins of something called the Orphan Chenab stream. So the Orphan Chenab stream is this stream of stars in the stellar halo that was discovered. It's a 60-degree long string. It's this string here that was discovered in SDSS. And most streams that are discovered, that had been discovered at that time, were dwarf galaxies that are getting sheared apart so they form a stream, or open clusters getting sheared apart so they have a stream. The Orphan Chenab stream has got its name because there was no parent open cluster or dwarf galaxy known for this structure at all. And so so one of the things that I was able to do is, in collaboration with a large number of folks, I actually used chemical tagging to try and find the origins of that stream. And from a chemical perspective, one of the things we were able to do was show that the stream itself chemically looks like a dwarf galaxy, not like an open cluster, not like a globular cluster, but it looks a lot like a dwarf galaxy. Again, I don't have too much time to talk about that, other than to just say, if anyone's interested in how you can use chemical tagging to discover the origins of structures like the Orphan Chenab stream, I'm happy to talk about that. Okay, and then finally, I think I have like 2-3 minutes?
No,
5
5 minutes.
minutes?
Well, we started 5 minutes late.
Oh. Well, I could tell you tons of things about the Orphan Chenab stream in that case. Okay. What I will do then in that case is tell you about the Orphan Chenab stream. I'll finish the Orphan Chenab stream, tell you about where I'm going next, and then close and then wrap up. So the Orphan Chenab stream was the stream that was discovered. No one knows what its origins are. Is it a globular cluster that's getting shredded apart? Is it a dwarf galaxy that's getting shredded apart? What the heck is this, or this stream of stars in the galactic halo? So what we did was we went to apogee, and we asked the question, okay, this is the Orphan Chenab stream in rotated coordinates of where it should be located. So the solid, or the dashed line is where I think the R Lyrae of the Orphan Chenab stream live. And so what we did was we basically selected a set of stars in apogee that have high resolution spectra, infrared spectra. We selected them to be near where the R Lyrae were, and to have radial velocities that were consistent with the Orphan Chenab stream. So its kinematics, spatial position, and distances are all consistent with the Orphan Chenab. And then if we plot up the alpha metallicity diagram, this is the alpha metallicity diagram. So this is metallicity over alpha over iron. So we saw this at the very beginning. Now remember, this is the thin disk of the galaxy. So high metallicity, low alpha. This is the thick disk of the galaxy. This is globular clusters in orange, and this is the Sagittarius dwarf galaxy. So you can beautifully see, right, the knee in the alpha metallicity diagram, it's flat, turns over. That knee of turnover is at about minus 0.7 for the Milky Way, because it's a high mass system. Sagittarius, however, is significantly lower alpha at constant metallicity because it is a low mass system. If you look at the Orphan Chenab stream, that's in red, they're even lower metallicity, or even lower alpha abundances at a constant metallicity. So if you take at metallicity minus 1.5, Orphan Chenab is at negative alpha over iron, Sagittarius is at plus 0.1, and the Milky Way is at plus 0.3, 0.4. So what this tells us is, number one, the Orphan Chenab stream can't be from a monometallic system because its metallicity ranges between minus 1.5 and minus 2, and 0.7. Number two, it has an increasing alpha abundance with decreasing metallicity consistent with what you find in dwarf galaxies. And number three, if you look at the aluminum magnesium, so globular clusters have this weird magnesium aluminum anticorrelation where they have very high aluminum and very low and relatively low magnesium. The Orphan Chenab stream is down here in red, so it's absolutely inconsistent with globular clusters. So what this paper says is that from a chemical perspective, from a chemical tagging perspective, the Orphan Chenab stream cannot be a globular cluster in origin. It's likely a dwarf galaxy, and the knee probably is at around minus 2, minus 2.5, somewhere in this area here. And that defines the limiting mass of about 1 × 10⁷ solar masses. So this tells us that the Orphan Chenab stream likely is made from a dwarf galaxy system that has to be smaller than 4NX in size. So that's the power of chemistry. That's the power of chemical tagging. You can actually just uncover the origins of previously unknown systems, like the Orphan Chenab stream. Okay? So that's some of the work that we've been doing in my group to kind of back out a little bit. We've been trying to answer big questions about how galaxies form using the Milky Way as a laboratory. The way we're actually doing that is using the tool of chemical tagging, and we've tested rigorously whether chemical tagging can work on long scales, on short scales, and so forth. And while I spent most of my career focusing on high-res spectroscopic abundances, as I've showed you throughout most of this, most recently I've actually gotten really excited about very low-resolution spectra, and that's all because of something called the HETDEX survey at UT Austin. So HETDEX is the Hobby-Eberly Telescope Dark Energy Experiment. It has absolutely nothing to do with galactic or stellar astronomy. HETDEX is based on, so this is the Hobby-Eberly telescope here, and the black boxes on these sides is an instrument that was named at the time. They thought it was a great name. Now it's actually a very terrible name. The name of this instrument is VIRUS. VIRUS is a low-resolution, massively multiplexed instrument. Each one of these boxes contain spectroscopic fibers, or fibers that lead to spectrographs. And in a single shot of HETDEX and a single shot of VIRUS, you can get 34,000 spectra, R of 750. Now, what they are doing is they are pointing they are pointing the HET up. It's a completely unbiased survey. They're just pointing it up, and whatever falls into the fiber, they're getting a spectrum of. They're doing an unbiased survey of Lyman alpha emitters to track dark energy. Unfortunately, they have to look at stars in the Milky Way because that's their contaminant, and they've been trashing the stars. And taking the phrase, one person's trash is another person's treasure, I've been collecting all the stars and using them for stellar galactic archaeology work. And it turns out, even at R of 750, you can actually derive stellar parameters and metallicities and alpha abundances. And that's seven and a half times larger than in resolution than BPRP from Gaia. But at least what these spectra allow us to do is to do a completely unbiased survey of the galactic halo. And one of the things is, since Hobby-Eberly telescope is a wide field now, it's been upgraded to like 22, 24 arc minutes. The next project that I have in mind is actually using VIRUS to look at resolved stellar populations in ultra-faint dwarf galaxies to map what those look like chemically, and then see how many ultra-faint dwarf galaxies the Milky Way might have eaten in order to assemble itself. So that's kind of where my research is going over the next couple of years. So with that, I'll leave it there. Just say that, for me, my research is what I've really focused on in my research is essentially trying to understand galaxy formation using the Milky Way and using very specific tests of tools like chemical tagging in the Milky Way to study how the Milky Way came to be and how it's evolving into its future. So with that, I'll end here and just leave up all of the summary.
Thank you very much, Keith. Very much appreciated that you gave this deep insight into how you actually do this magic of digging out stuff from the Milky Way. I'm sure we will have questions both from the floor and also from Zoom. Could I ask the Zoom audience to either raise their hands or write a question into the chat? And while you're sort of doing that, I'll ask the first question, Francisco.
Yeah, thank you very much for this nice talk. I have a question. When you are using the wide binaries as test cases, of course the primary orbital parameter separation, of course, but I wonder, does anything change and correlate with the eccentricity of the binaries? Because for two reasons, right? One, because maybe the binary was not a native binary, and one because the orbital separation is different different points. So maybe something changes with that. Do you see such effect in your analysis?
Yep, that's a good question. So for the wide binary study, you can imagine delta metallicity as a function of, we made it as pair separation, but you can imagine changing that axis to eccentricity. I think we did make that plot, but I don't think that there was not a large range in eccentricities for the pairs that we studied. It would be interesting, I think, to target fairly eccentric and not fairly eccentric binaries to ask that question. The other thing that we've been interested in regards of what may make stars not chemically homogeneous is not just whether it's chance alignments or chance captures, but also are there engulfment scenarios like planet engulfment, which is what they claim in Cronus and Creos result, that could also cause the atmosphere of one star to look different than the atmosphere of the other. The telltale signatures for that are that the difference in abundances correlate strongly with condensation temperature of the elements. The refractories that go into building the planet cores is enhanced, and the volatiles that go into the planet atmospheres are not. That's something that is still, that's actually a project that we have in mind for DR3. When DR3 is released, one of the first things we're going to do is actually look at all of the wide binaries and the refractories versus the volatiles to see if we can see planet engulfment evidence. But it would actually be very exciting, I think, to look at the eccentricity distribution as a function of delta, say delta x over Fe or delta Fe over H.
Okay, any more questions? One at the top. Wait a minute.
The wide binaries. So, and do you think, can you know or can you constrain the origin of that wide binary from the chemical tagging?
The origin of the wide binary.
Yeah, formation. There are several formation scenarios from, someone say they form from the triple or more system, or yeah.
I think from chemistry alone, it would be difficult to do. One would want to validate that, I think, with a kind of test like looking at the orbital eccentricities, or the orbital properties of the wide binary with the chemistry together to say whether or not different formation channels lead to different chemical abundance patterns. One thing I would say is that the fact that we see co-moving pairs that are separated at very large separations, at parsec level separations that are still homogeneous, I would not be super optimistic that that would work, because I would have expected that as we go to larger separations, what's making the wide binary is likely more chance encounters. You're going to see higher probability of chance encounters on chance alignments than you would at very small separations, but we don't really see significant differences in the chemical patterns, or the delta chemical pattern rather. So I wouldn't be super optimistic, but I would be potentially excited by looking at the orbital properties as a function of delta x over H to see whether that's possible or not.
While I love binaries, let me ask a question about another aspect here. You showed beautifully that stars born together, at least in a large majority of cases, have identical abundances. Now, there are people that, like Melissa Ness, who says, well, most stars born at the same radius at the same time look alike. So in this sense, even if you had near infinite precision measurements, you may not be able to do the strong tagging, which means who was born in which house. Do you want to comment on that?
Yes, so that goes back to this slide that I put up. There are two underlying requirements of chemical tagging. The one is the chemical homogeneity, and we've tested that, and we've done so semi-regularly. We tried the best that we can with high res, high signal noise, all of that. The second one is the one I didn't talk about, which is the uniqueness. And that's a question of chemical doppelgangers. And so Melissa's written a nice paper on the chemical doppelganger rate with apogee. I think it is true that stars that are born in different locations, but at the same radius, different azimuthal locations, are probably fairly similar. But what we should do is actually go back and reconstrain the Doppelganger rate as a function of galactic position with the data that's coming out now with both DR3, because DR3 will have abundances embedded, but also with the updated apogee and updated Gala parameters and abundances, for example. So I think that, I think strict, strong chemical tagging, I think is going to be nearly impossible. That's my guess. But I've been very careful to be agnostic, because I know people on both sides.
Okay. Thank you. I think we must slowly wrap up now. Before we do so, can I ask if there are any questions from the virtual audience? Doesn't seem so. If I may just be permitted to ask a sort of left of field question. What is known about the chemical abundances at a particular galactocentric radius and a particular height of metallicities of stars as a function of the mass of a cluster in which they're formed? You know, naively, you have to get a lot of mass into a compact region, and then there'll be feedback effects which change the metallicity of the natal gas as a function of that. Is anything known at all about that? And, you know, could that give some dispersion into this, what Hans Walter was talking about, this sort of overall metallicity?
Absolutely. I think it's a little bit tricky because the parameter that's, I think, most important here is age, actually. So it's age, mass, and what the gas has seen.
Right, but I mean, if you can look at young stars in young clusters, which I know is difficult to do.
Yeah, it's quite difficult to do. From a chemical perspective, it's difficult because of the data. Young stars do not behave well for doing galactic chemistry, stellar chemistry. But in principle, one can begin to ask questions about, given a specific location in the galactic disk and a specific age, you can begin to ask questions about what the chemical enrichment at that location had to look like to give you the population of stars that you see in that cluster. It is still a little bit tricky to do, in large part because there is both mixing of stars, but also mixing of gas. So one of the things that that comes into this is on what scales are these structures being formed. That's going to be dependent upon mass, and those scales also one has to compare those scales with the so-called correlation lengths of the elements, where different elements can be well mixed on different scales. So iron and iron peak elements, for example, are well mixed on large scales because the energies required to do that for supernova mean that the gas can be very well mixed on very large scales, whereas AGB stars produce S-process elements, the energies are much lower, so those are mixed on much smaller scales. So there's a lot of complexity there, I think, with mixing scales in the ISM, with age, and with location of the galaxy.
Fascinating, thank you. Before we thank Keith again, I think we'll finish the colloquium. I have a couple of announcements to make. That's it. And finally, I'd like to announce next week's colloquium by Anna McLeod. She'll be talking about feedback due to young massive stars on the interstellar medium and on galaxy evolution as a whole. So, let us now thank Keith for this very interesting colloquium.